Hello and welcome back to Calculus 3. We are continuing our chapter 12. That's a 12.3, limits and continuity. Before we do any of the Calc 3 stuff, let's go back to Calc 1 and just see what the limit is, because we don't want any issues. Even though half of your Calc 2 was just taking limits. But do we actually know what it is? So, if you go and take a look at f of x equals x squared, you know what the graph looks like, and you know, hopefully, that f of 2 is 2 squared, which is 4. So you draw that and you say, all right, if my input is 2, my output is 4. So this is your good old pre-calculus when you compute the input, right, and you get the output of 4 and done. And then Calculus 1 came along and said, well, we can do better. If you say limit of x squared as x goes to 2, it's going to compute the same thing. Limit essentially computes the y value of a function. That's the cheapest possible sentence concept you can say about the limit. What is the limit? A fancy way to compute y value and you're done. Now, why we say fancy way? Why is it different? Well, see, your pre-calculus, which is this, computes at the point. So pre-calculus computes at the point. Limit computes everywhere else except at the point. So limit computes everywhere else but at the point. So that's that. So now what does that mean? Well, we approach from the left. As you approach from the left, these x values give rise to y values which trace the function going up, which traces the y values going up towards 4. You approach from the right, you will have the same thing happening. We're going down, we're going down. What happens is that as you are walking closer to number 2 on x-axis and you are computing y value for each step you make, you see that the y values are squeezing around 4. So we actually have now the chart of values that we have to consider to compute the limit. Limit is never computed by plugging in 2 into the function, because function might not be defined for that point at all. Pre-calculus would instantly fail in that case, and the limit might still give you the value. So the way the limit computes is the limit says, all right, I want to see what's happening at 2. So give me the, 3 or 4 values from the left and from the right and see what the trend is. So you maybe start at 1.9, then 1.99 is closer, and then 1.999 is closer still. So, right, so you were 10 cents away, then you are 1 cent away, then you are 1/10 of a cent away. On the other side, the same thing, 2.1, 2.01, and 2.001. When you compute these values, you will see that they squeeze into 4. So let's do some of these calculations because we can. What do I have over here? Come on, there we go. So 1.9 squared is 361. That's not 4, that's 361. But then 1.99 squared is 3.96. You see, as x values, good effort, as x values go to 2, the y values should go to 4. Okay, 1.999 squared is 3.996. So I hope you see that it went from 3.6 to 3.96 to 3.996. So you see how the values are marching towards 4 from the left. 2.1 squared, so we do the far one. This is 4.41, right? That's well above 4. But then as soon as you go 2.1 squared, that becomes 4.04. Now that's closer, right? You were 41 cents away. Now you're only 4 cents away. And finally, 2.001 squared is going to be 4.0004. So now you're 4/10 of a cent away. So this is what the limit is, the essence of the limit. The limit doesn't care what's happening at 2. The limit computes at all infinity of the points around 2 and then just infers, oh, that's what's happening at 2, because all of the other infinitely many points around 2 are pointing that the y value should go to 4, right? Without actually ever computing this. Now, for our practical purposes, we compute the limit by plugging the number in, unless something goes terribly wrong, like denominators are 0 or whatever else. In that case, we use some different witchcraft, which would be algebra or graphs, charts, so whatever else we can do to get the problem solved. So, yes, we actually plug in the number to compute the limit, but we are not supposed to. We are not supposed to do that. We are supposed to get the value, right, of the limit by computing at infinitely many points around the value rather than at the value. So that's the review of the limit. Now we move to the two-dimensional limit, and we understand it is the same thing. Your domain is now, instead of just being x, your domain is now xy, and then you have some kind of a formula where you get to compute this. We are going to have the same correspondence as before. Some limits you will be able to compute just by plugging values in. Other limits you will have to work out using algebra. And then other problems you will actually have to find the way to say, well, limit does not exist. So we start first with the standard definition, the epsilon delta definition of the limit. So now we're talking about limits in R3. So we have the definition here. So limit xy goes to ab of f of xy is equal to the limit L. I have to put another one here. So one more limit as point P goes to point P0. Alright, that's just the same thing, different notation. Okay. If given any epsilon larger than 0, there exists delta larger than 0, such that, and now we have our standard f of x, y minus L in absolute value is less than epsilon whenever 0 is less than the magnitude of pp0, which is the square root of x minus a squared plus y minus b squared. A is less than delta. This is the standard definition, right? And the way this works is it actually creates a tube around the region that you are looking to find the limit for. It's a little bit tricky. Let's see if we can fashion something here in terms of the graph. So I have some kind of a surface, right? Whatever it is, it's a surface, and this surface here, how about, okay, let me try. All right. So this is a surface. This is over here is a little bit elevated, right? And then it changes, right? So there is this like a hill, right, that you have to hop over. So this surface is given by z equals f of x, y. And I want to know, here is the point. So I'll call this point AB f of AB. So it has AB coordinates, right? Because it's going to be somewhere in the xy plane, that's AB. And then because it's on the surface of the shape, it's going to have f of AB as the z coordinate. So it has AB f of AB for the surface. And this is our equation. So now what is the limit? The limit is going to create, as you can see, in a domain, this is a circle, right, with the radius delta. So it creates this disk. It creates the disk around AB. And now that disk is like a tube projected up, and it's going to create some disk or a shape on a surface of this. Now, what's going to happen is that these values are going to project onto the z-axis, and they will create a tube, so not the tube, they create a range. So this is your limit L, right in the middle, that's what you're looking for. And these other values are L minus epsilon and L plus epsilon. And over here, I'll just say delta. Delta is the radius on the bottom. So what happens is, as you squeeze this radius on the bottom, this range would squeeze into L. That's actually what's happening in the case of the limit. But again, what is the limit? Limit is just a fancy way to find the z value in this case. So as you are solving basic limits can be computed by plugging in values. Now that fails immediately when you get 0, right? Denominator and all that kind of stuff. So now, if you have an example, limit xy is going to -3, 1 for the function x squared y minus e to the x whatever. There we go. That's good enough. Right? When you take a look at something like this, you say, well, all of these functions, none of these has the denominator and the vertical asymptote and all of that kind of stuff that can ruin our day. So you can plug in. It's going to be -3 times 1 minus e to the -3, and the whole thing becomes -3 squared. So that's a 9, thank you, minus 1 over e cubed. That's a number. You can go and you can get decimals. So when it's this basic, right, no denominator equals 0 or anything weird happening, then plugging in is still what we can do. So that's the most basic stuff. However, things become interesting very quickly here because most of our limits are not going to be calculated this way. So let's take a look at some properties of limits before we take a look at what we call boundary limits and other stuff. So limit laws. And I'll just say same as in R2. So what do we have? We have the sum. So limit of xy going to a, b of f of xy plus or minus g of xy is going to be the sum of these guys independently. So limit of f of xy plus limit of g of xy. Obviously, you still have the xy goes to ab and xy goes to ab. So this property is there. Now this is in a book, property 1 and 2. Now property 3 is the constant multiple, which says that the limit of xy going to ab of c times f of xy, you can keep constant outside. This rule has been with you forever. And then just focus on the limit of xy. 4 and 5. So we have product and division. These do not work for derivatives, right? They only work for limits. So limit of f times g is the limit of f times the limit of g. I'm shortening this now. I'm not writing the denominator and of x and y. The notation is given up there. So this is the limit of f divided by the limit of g, provided that the limit of g is not 0. And finally, 6 and 7 combined into the limit of f raised to any kind of exponent m over n is going to be, you find limit of f first and then you raise everything to m over n. So these are the limit laws. I compressed 1 and 2 into a single line because I put plus and minus there, and I also compressed 6 and 7 into a single line because line 6 just gives you the same thing without over n. But since it works for both, why not combine them in one? So there you have it. Those are the limit laws. And now we can start talking about the interesting bits. Definition. So, which means it is possible to find a disk centered at P that consists only of points of R. Only points of R. Q of R lies on the edge of R in the sense that every disk centered at Q contains at least one point in R and at least one point outside of R. Now, these words might not mean a lot until you draw a disk around it. You see that each point of this disk is within R as well. So you can draw the disk bigger, you can draw the disk smaller. There's no limit on how small you get to draw the disk. Now, for point Q, that is on the boundary, on the edge, when you draw a disk, you'll see that some points of the disk are inside R and some points of the disk are outside of the R. R being our 2D region. So that's simply what these two definitions are saying. So interior point and the boundary point. Interior point is the one that is in the region, and the boundary point is the one on the outlining line on the boundary. So now we have another definition here. We'll say this one is green. Our region is open if it consists entirely of interior points. Our region is closed if it contains all of its boundary points. So armed with this knowledge, we can talk about limits at boundary points. This is where you get your denominator to be 0. And you have to deal with we have to deal with that. So an example, without me hunting, can I? Whatever. Without me looking for 15 minutes and waiting for the book to load, I'll quickly explain the one that it's in the book, even though you know I don't like that. xy minus 4y squared square root of x minus 2 root y. Okay. The first instinct when you see the limit and you need to compute the limit is to plug in the numbers. If you get an answer like 7, right, you're done. If you get 0 in denominator or anything weird happens, well, you can't plug in. You have to use different methods. Different methods include rationalizing, they include algebra or whatever form, factoring, canceling, and all of that kind of stuff. So now our first order of business here is to just plug in 4 and 1 and hope that that will solve the problem. Unfortunately, it will not, because the denominator becomes 2 minus 2, and you get 0 in denominator, so we cannot plug in. Let me write that in blood. Cannot plug in 4, 1, because denominator equals 0. And that's an issue. So anytime, I don't care, calculus 1, calculus 3, calculus 17, whatever you have, anytime when your denominator equals to 0, when you plug in a value, that method doesn't work. So you have to figure some other stuff. So what else could we do? Well, in this case, I can do a lot of factoring. So we have the limit, and I can kick out y in the numerator and have x minus 4y divided by square root of x minus 2 root y. So all I did is I factored out y. Now, if you are not familiar with the fact that you can factor anything, now is the time to get familiar with the fact that you can factor out anything. You can factor out x minus 3. It's very simple, right? If you rewrite this as square root of x squared minus square root of 3 squared, now it's just difference of squares, right? And you can write this as the square root of x minus square root of 3 times square root of x plus square root of 3, right? That's basic algebra. You haven't seen it before, most likely. But you can factor whatever you want as long as there is minus in between. If there is a plus, you're going to get complex values there. So all of these guys would have i's over here. Well, not all of them. The root 3's would. So in that light, I can factor this. And you see that I'm going to get exactly what's in the denominator, and then they will cancel. Now, some of you would say, well, can't you just rationalize? Yeah, but this is far cooler than rationalizing. So, y times square root of x minus 2 root y times square root of x plus 2 root y divided by square root of x minus 2 root y. These die. And you are left with the limit as xy goes to 4, 1 of y times square root of x plus 2 square root of y, from where answer is obviously 4 when you plug the values in. 2 plus 2 times 1, that's 4. So we can rationalize, we can also factor. And those are your two main techniques to solve. Now clearly, right, if the stuff is not working out, you can always revert back to chart of values. Chart of values. And the chart of values, you should, you have to be a little bit careful about chart of values in this case, because as you are going to see in about 5 minutes, the approach matters. And that is something that if you are to use the chart of values, like we used chart of values here, right? This is the table of values, chart, whatever you want to call it. If you are going to use this, you have to be very careful. Guys, on x-axis, you can only go left or right. You only get to pick x values. On the xy plane, you can go in any direction you want. That gives you infinitely many different ways to approach your number 4, 1. So, when I draw the domain xy, this is my point of interest, 4, 1. I can approach that if I have a line starting from the origin, approach like that. Right? But now, that could be also a vertex of a parabola. And I can approach like this. It could also be a point where you start your negative cosine and go like that forever. Right? There's your approach. For more exotic cases, you can spiral in if you want to. It doesn't matter, right? Under every approach that you pick, you must have the same value. Calculating limits in Calculus 3 is really, 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 really pain in the neck, because you have infinitely many ways to approach. When you are on the x-axis, to approach number 2, you can approach on the left, you can approach on the right. You have to be on the axis. There is no degree of freedom of any kind. You just go from the left and from the right, and you're done. Now, what we have to have happen here is every approach you pick, which is infinitely many of them, each one of them has to give us 4. And that is a little bit tricky. But at least, you know, we can verify this 4 using one of the approaches. So let's just use an approach in a table of values to see, and for the simplicity, yeah, why simplicity? Let's just make it as difficult as possible. How about it? Let's use the parabolic approach. What is the equation of this parabolic approach? I'll call this g of x, right? Well, just g of x is, we'll keep a as 1. So this has to be x minus 4 squared plus 1. Right? The coordinates of the vertex are 4 and 1. And those are your agent k. And you have to have a quadratic formula there. So there's your approach. So you will be approaching along this line, and you are approaching the point over here, which is 4, 1. So now, this function will generate all of the y values that you actually need to calculate your chart. Because, remember, your function was z equals, whatever the limit was, holy nightmare, it's x, y, who came up with this? Minus 4y squared divided by square root of x minus 2 root y. That's your z. As you can see, you have to feed x and the y. And you have to feed x and a y that are close to 4, 1 that you're looking for. So what am I going to do? I'm going to pick my x's, g will give me y's, and then I have x and a y to plug into z to come up with the first value. Huh? Not yet? All right, let's see. So let me just one more time. All of this stuff over here is the domain. And over here is going to be range, which gives us the limit. And domain gives us the input for the chart. So let's start. I know that I will be computing the chart is obviously now set up differently because it's larger. I want to know, so these are my x values, y values, and z values. So I want to know what's happening when x is 4 and this is 1, what's happening with the z. That's where the limit is. Now I get to pick my x's and then I have to compute y's and z's. So pick my x's. So x 3.9, sorry, wrong. I have to start from the other side. So 3.9, 3.99, and 3.999. On the other side here, I have to start at 4.1, 4.01, and 4.001. So as you can see, I am still picking the same way like I pick in Calc 1. Well, now in Calc 3, the y value of the approach will depend on the approach you want, which in this case we said parabola. So these guys, y is equal to, we have our equation x minus 4 squared plus 1. So all of the y calculator. So you first go into the function and you plug your function in, which is x minus 4 squared plus 1. And then, second quit, vars, y vars, f1 of 3.9. That gives you 1.01. Second entry, 3.99. That's 1.0001. And finally, 3.9. Second enter. 0.999. 1. It's way too many zeros over here. There we go. Same thing from the other side. So second entry. .1 is going to give, oh, this parabola, these are symmetric. Why am I typing this? So these are symmetric. So now I have my ordered pairs. These guys get plugged into z of xy. Now that is really annoying because now we have to plug in everything. And unfortunately, our y-vars in the calculator works only for one variable input, so calculator cannot help us to solve this, very quickly. So let's see. When x is 3.9 times 1.01 minus 4 times 1.01 squared, so that's the numerator, close parenthesis, divide, open parenthesis, square root of x, which is 3.9, close parenthesis, minus 2 times square root of 1.01, I get 4.025025. 4.025. So that's the value that I have. Remember, it's going to go to 4 because our answer is 4. So now if I compute the next one, it is going to be better than this. It better have a closer value to 4 than 0.025. So now, second entry, and I'll go and times, this is instant regret. Such is life, right? So minus 4 times 1.0001 squared, close the parenthesis, divide by, open parenthesis, square root, kill me now, of 3.99, close the parenthesis, minus 2 times the square root of 1.1230, close, close. Ugh. Something is terribly wrong because I got 2.6. So 3.99 is 1.1. 001. I dropped the 0 there. Great. Second entry. Second insert to 0. So now we have 3.998. Well, that's closer to 4. Than where we were before, because we used to be 2.5 cents away. Now we're 0.2 of a cent away. So as you calculate these, they will go closer and closer and closer. So these numbers must converge into 4, and the numbers from this side must converge into 4. So the same method, the same very tedious method of calculating this limit works. However, it's very, very painful and very long to compute, and also it's not guaranteed, right? The answer is not guaranteed because you have to check all infinity of approaches, right? And if one of those fails, the entire concept fails. And that's the last part of the limit portion. So we start by when is the case when the limit does not exist? So just a quick review. In Calc 1, one of the most important theorems of the lifetime said that, so in Calculus 1 we said that if the limit of x goes a from the minus, right, a minus from the left of f of x is the same as the limit x goes a plus from the right, f of x, is equal to L, then the limit of f of x as you approach from both sides simultaneously, right? So just x equals to a is equal to L. So this technically said that if the left and right limits point towards the same number, the overall limit is that number. Otherwise, limit does not exist. So this is what we have in the calculus 1. So now going to calc 3, I'm going to say all paths taken to compute limit must give the same z value. So that means no matter which approach I take over here, whether it's a trigonometric approach or with spiral in or whatever, no matter what I do, all of them have to give me 4. If one or more approaches gives a different value, limit does not exist. So that means that if I am to compute with a parabola and I get 4, and then I compute with cosine and I get 4, and I compute with a linear line and I get 4, I take a whole bunch of these and I try 50 different functions and they all give me 4. And then I try a 51st function and I get 6. The limit doesn't exist by this theorem. So now your job is to figure out which path is to be taken so that the limit ends up being a different value than from the path previously taken. Now, since you live in a 3D space, and we are the large scale, right? We are not electrons who do not obey these rules. We pretty much have, I don't know, you just went to the bathroom. You came back, right, or whatever, right? You came back here. Were you expecting this to be any different place? No, right? So if you guys go to the bathroom, you go to the right. If you came from the parking lot, you came from the left. You walk into this classroom, it's this classroom. When the limit doesn't exist, that means when you walk from the bathroom way, right, this room is 311, and when you walk out from the parking lot way, this classroom is North Pole or something, right? So this is what no matter which path you take, you have to end up at the same location. That is what the limit simply says. Now, limit doesn't exist when two different paths give you different locations. So as you can see, in this classroom, we have about 25 students, right, including me. That's 25 different paths, unless any one of you live together, right? I know none of you live with me, so at least my path was different than everyone else's. We all took the different path, and we all ended up in this classroom. The limit of this function of us getting here is this location in space, right? And we say that limit exists, right? And all infinity of paths would have to lead to this location in space. So now, the next question is, how do we detect efficiently, how do we detect that there is no limit. So, again, I'm going to discuss the problem that is already done in the book, because your homework, believe it or not, has 4 problems. And if I solve those 4 problems, you have nothing to practice. So, please practice as much as you can. So, we have to have all paths lead to this. Now, guys, path is simply y is a function of x. So if I pick a path, y equal f of x, I collapse this calculus 3 integral to a calculus 1 integral, limit. I collapse the calculus 3 limit to a calculus 1 limit. If I pick any path, let me pick a path y equals x. As soon as I pick path y equals x, my limit collapses down to just x equals to 0, because y and x are the same, they both go to 0. In the numerator, I have x plus x squared, and in the denominator I have x squared plus x squared. So the whole thing collapsed onto a calc 1 integral. So now I have limit x goes to 0. I have 2x squared over 2x squared. They're much different, right? The top is 4x squared. The bottom remains 2x squared. These dies, and the answer is 2. So limit is 2. Now, you would say, well, the limit is 2, but I say, hold on. Well, maybe your limit is 2. I don't know. But if I get anything else other than 2, well, by the theorem up there, limit does not exist. Because we took a different path to get to the same location, and location was different, which is no bueno. Right? So currently, you are telling me that the location is 2. Like a classroom. Number 2 is that location. We got to that location by walking along this line, y equal x. Now I'm changing the line I'm walking at, right? Oh, be very careful that the stuff that you're picking is going through the point that you are assigned. You can't pick x plus 1. X plus 1 doesn't go through 0, 0, so the whole thing is pointless. You limit, again, x goes to plus, good effort, 2x squared. So now this is limit, x goes to 0. 3x squared divided by x squared plus 4x squared. I hope that you see that the limit over here is 9/5. Right, 3 squared is 9. So you have 9x squared in the numerator, and you would have 1 plus 4, right, is 5. X squares drop, and now you have 9/5. So 2 and 9/5 are not the same number. Therefore, limit does not exist. We found a path that gave us a different value. So, because it's that in order for limit to exist, all of the paths have to come up with the same value. How many paths do we have? Infinitely many. You pick a cosine path, I pick the sine path, then you pick a hyperbolic tangent path, then I pick the quadratic path, then you say, okay, but can I use the square root? Sure, you can use square root. Right? All of these paths must go through 0, 0 in this particular problem. All of the paths had to go through 4, 1 in the problem before that. You saw me set up the parabola through 4, 1, with 4, 1 being a vertex. It doesn't have to be vertex, but I made it a vertex because it makes calculations cheaper. So what is the ultimate way to check all of these at once? Here, in blood. Pick y equal mx. That's the boss move. Right there. Why is it a boss move? Because you are checking infinitely many approaches in a single calculation. That's why it's a boss move. Here's the definition for the boss move. We are checking all linear approaches in one calculation. If the answer has M in it, then value depends on the path taken which implies no limit. D&E, right? We can actually use this boss move on the problem we just had. Limit of x plus y squared divided by x squared plus y squared as xy goes to 0, 0. Again, guys, this is situational. Y equal mx passes through zero, 0. This is very important. It has to pass through the point that you are looking at the limit. Otherwise, it doesn't work. So, now, you have every possible approach where slope is 1, when slope is 2, when slope is 3, when slope is 4. You see that? So it's infinitely many approaches. They're all there. They're all of them, positive, negative, because this m can take on any value. So I plug that in. I get limit x goes to 0 of x plus mx squared divided by x squared plus mx squared. And you just shovel through this algebra, and you end up with a result that depends on m. So what do I have on top? I can kick out x squared, and I'm left with 1 plus m. No, lies and deceit. I can kick out x squared, and I'm left with 1 plus m squared. On the bottom, I have x squared plus m squared x squared. When you factor out x in the denominator, like this, you get 1 plus m squared. These now die, and you're left with 1 plus m squared divided by 1 plus m squared. They don't cancel. I'm going to write it here. 1 plus m everything squared divided by 1 plus m squared. This does not cancel because the top is m squared plus 2m plus 1, and the bottom is just m squared plus 1. They are not the same. There is a, right? There is the 2m term that you have in the numerator that you don't have in the denominator. So you can do the long division, but you're not going to get far. They don't cancel. So here it is. Answer depends on m. That means m was the slope. Remember that I used y equal x and y equal 2x? That 1m and 2m, 1x and 2x, that 1 and 2 are m's that I used before. So for the problem, for the path we did over here, right, y equal x, m is 1. And that m produces 2. For the next pick that I used, m is equal to 2. And that gave us 9/5. If you use 1 and 2 on this formula, you are going to get 2 and 9/5. Try it. If this is 1, that becomes 2, And if this is 1, that becomes 2. So 4 over 2 is 2. If n is 2, you get 2 plus 1 is 3, squared is 9, and then 1 plus 4 is 5, 9/5. I mean, that's that calculation. So I know that at least one of the 4 problems that are assigned in the textbook, and you should look at all 4 of those, at least one of them will give you that if you plug in y equal mx, all of the answers are the same number. Does that mean that the limit exists? Because all m's gave you the one same number? All approaches were the same number? Yeah, I'm asking a question. I know for the fact that one of the 4 homework exercises on this, when you plug in y equal mx, the answer will not depend on m. Does that mean that that's the limit? Whatever you get, you'll get, I don't know, 7. Well, we don't know. All it means is that all linear approaches are giving you 7. Have you tried the rest of the infinity of possibilities? At that point, no, right? So this is very interesting stuff. So spend some quality time with it. The second part of the title kicks in now. It's called continuity. Right? Did I mention that this lecture is 7 hours long? Yes?
Professor, would the limit ever exist if you have something like this?
There are other ways to check that. So, yeah, such is life. Okay? Continuity. I should just end this by writing over here the same as in R2 and just move along. But then, since I'm the best instructor in the galaxy, I'm going to write out the stuff, right? I know it's objective. It shouldn't be. Definition. Continuity at the point P. So, z equals fxy is continuous at P if, and then we have 3 rules. They are the same like in Calc 1. F of P exists. Maybe, actually, to make this one, let's define P as x0, y0, and then I can have a better notation here. So if f of x0, y0 exists, number 2, if the limit of f of xy as xy goes to x0, y0 exists. And finally, number 3, if 1 is equal to 2. So you have to have these 3 satisfied in order for your limit to exist. The limit doesn't exist at the edge of this desk, right here. Because if you are approaching from this side, right, the desk, you are going to hit the bottom of the desk. If you are approaching the same edge from the top, the limit is this. So the same xy point that you are observing from the bird's eye view on the domain that's just x0, y0. x0, y0, which is a point right here, has no limit because approach from the bottom and approach from the top, there is this vertical gap. One says the limit is 0. The other one says, approach, says limit is 3. And they don't agree. If the limit is different, when we know the limit doesn't exist, which is the reason why things fall. It's not continuous path. Please observe that any other point over here leading up to this point of discontinuity is perfectly continuous. You don't see this falling anywhere, right? This is continuous. The surface of this desk is continuous. The surface of all of your, well, you have these pits and things in your desks, but say for like everywhere else other than where you have these holes, right? And some of you have these things broken or open. Any one of those, right? It's continuous, 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 and then, right? The same thing happens here. Continuous, 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 right? Every point is continuous, and then point of discontinuity. There's a hole inside the desk, right? It's gone. This is the way to mathematically describe a cliff. This is what a cliff is. You have one z value from one side, another z value from the other side. It breaks number 2. When it breaks number 2, well, immediately you can't have number 3 either. So if any one of these 3 gets eliminated, right? In that case, you don't have the continuity. Continuity is pretty important because we construct bridges and parking garages and, you know, the third floor. You can't construct the third floor without actually having the second floor constructed. How many times as a kid someone tells you, well, you know, you learn mathematics, you have to learn in order. You know, you have laid a foundation first, which is algebra, then you raise your walls up, that's your functions and pre-calc, and then you can talk about the roof, right, which is calculus. Yeah, you don't get to start building a house roof first. Even though that has been my dream since I first heard that argument. It is completely possible. Just have helicopters hover and hold the roof for whatever amount of days you need to build the rest of the house underneath that. I mean, it's completely possible, right? Which is also how some people pass calculus without knowing basic algebraic rules or knowing definition of a function or how to work with the inverse, right? They still somehow make it miraculously to calculus. Those are the people that defy the rule of, yeah, you can build a house any way you want. It's just more expensive, right? It's a lot of fuel and stuff for these helicopters to hold this thing up. And then you just build on your way down. There's always a way, right? What does it say? It's impossible until someone does it. And then it's like, oh, okay, yeah. It's obviously can be done. It's, you know, Joe did it, so. It's Joe. Good. Now, this is continuity at the single point P. I was focused on a single point right there, and the bottle fell when it got there because my flat surface, my equation of the plane was continuous everywhere, and then it got to the edge, and the whole hell breaks loose, right? Goes right down. So now the discontinuity happened at the point. So now, what is global continuity in that case? So another definition follows. Z equals f of x, y is globally continuous if it is continuous at each point of its domain. So, guys, the domain is some 2D region in XY plane. Please observe that any object you can possibly think of has a shadow on the XY plane. You have a shadow on the XY planes, the chair, the desk, that is the domain. If you pick any point underneath that domain, and there is some function z equals f of xy that describes the shape of this, you will plug that x, you will plug that y, and you will come up with a point z and another point z and another point z, which all of those points will create this surface. Whether it's a desk, very easy, write z equals to 3, pick any value you want, right? It's always 3 because it's a plane, right? That will be surface of the desk. So each one of those points in the domain gives rise to z because you plug those x and y into here to compute your z's. So if it's continuous at each one of those points individually, and there are infinitely many of those, then you have the global continuity, which means that the plane is continuous. Is the desk continuous? Yeah, wherever there are no holes, right, or edges, it's continuous. Now, this desk, as you have seen, right, there is a hole right here, right? So this one is not continuous everywhere because there's a hole. There's another hole right there. And that's the hole where the discontinuity happens. The holes in bridges and, other things, they create discontinuities, and then, right, stuff breaks. So that's the definition of continuity, and we have all of the same rules as before. The functions are continuous if you add them, subtraction. So let's write that. Some rules. Let f of xy and g of xy be continuous. Then, and now I have f plus g, f minus g, f times g, f divided by g, as long as g is not 0, f squared. Let's put f to the n over m, so take care of all of them immediately. And here is the cool one, f composed with g are all continuous. So this essentially says any combination of two continuous functions results in a continuous function. So any combination of continuous functions results in a continuous function. So if you add two continuous functions, you get a continuous function. You compose two continuous functions, you get a continuous function, and so on. Now that's very useful when you are trying to deal with the continuity of some really crazy expressions. You just break them into smaller parts and you deal with it. Depending on which Calc 2 you took, but in Calculus 2, when you did your integral test in sequences and series, right, test for series, you were supposed to check test, right? That was integral test for Calc 2. You had to do that proof, and then when you get that crazy function, well, this is the fastest way to do the proof. So now, if you are asked if the, so let's say z equals to sine xy divided by x squared plus e to the 4y, right? Is this continuous? The answer is hell yes. But then you have to do all of these, like it's a paragraph to do it. You start by xy is continuous because it's polynomial, like, right? So it's a plane. It's not a plane. Sorry, it's a polynomial like. Right? You just have x times y. They're both continuous, right? So xy is continuous. Then sine xy is continuous because of f of g, right? Then x squared is continuous. That's basic. E to the 4y is continuous. That's also basic. That's all from Calc 1. Then we say x squared plus e to the 4y is continuous because f plus g from the blue theorem. Finally, we have that sine xy over x squared plus e to the 4y is continuous because f over g, where g is not equal to 0, and we know that because x squared, so because x squared is always positive, unless x is 0. So this is not continuous at 0. No. This is good. And e to the 4y is always bigger than 0, so when you add them, it will be bigger than 0. So sum is always positive. There we go. This is the standard. So your exam question could be something like this, and then you just have to write a paragraph. So we know that xy is continuous. Those are polynomials from Calc 1. That's fine. And then sine xy, well, that's now compositional functions. That's in the blue theorem. And then you have your x squared. That's, again, Calc 1. We know it's a polynomial, so it's continuous. E to the 4y, well, that's also continuous because, again, Calc 1, all exponential functions are continuous. And then the addition, again, blue definition up there. So you just go one by one. The answer is, in this case, a paragraph. So function is continuous. You also have to make sure that the denominator is not equal to 0. If that was x squared times e, it would fail because x could be 0, and that could kill e, right? Because 0 times whatever number you get here. E is always positive, right? Because it has a horizontal asymptote, so it never falls to 0. So you will never get the situation where you have 0 plus 0 to have denominator equal to 0. You will only have positive values there. So in this case, what we have is the function is globally continuous everywhere on its entire domain. Now you might say, well, what is its domain? Well, that's a different story, right? That's 12.2. I mean, it's obvious that it's all real numbers, but because you can plug in positive and negative for x and y, and they will not produce complex numbers or 0 in denominator or anything like that. So this is actually continuous on the entire R2 domain, on all of its infinity. And that is 12.3 after 2 hours. It was a quick section, right? And now we say bye.